In this video, we're going to do some practice problems relating to the definition of the definite integral and looking at Riemann sums to approximate the value of the definite integral. So our first example is estimate the integral from 0 to 2 of x squared minus 1 dx by calculating a left Riemann sum with n equals 4. So before we actually do the Riemann sum, let's think about this graphically. We should know how to graph the function x squared minus 1. It is the parabola where we move down 1 unit. So it's going to be something like this. Parabola just from 0 to 2. We could graph the rest of the parabola as well, but we only care about from 0 to 2. And we're looking for the area from the function to the x-axis. Let's actually shade what area that's going to be. We're going to be looking for this little area from the function of the x-axis. That's going to be negative. And we're going to look at this area from the function to the x-axis above. That's going to be positive. So let's remember this is going to be a negative area. And this is going to be a positive area. So let's talk about why this idea of a Riemann sum is important. If you tried to find that area, that's not a nice shape to find the area. We're going to see in an example in a little bit that we can find area just by looking at nice shapes. We did that in the previous section as well. But this is a curvy line, and we don't really have a formula to find that area yet, but we can estimate it with rectangles. So I want to make clear that also we do not need the picture for this problem. And I don't want you to think that you have to draw a picture of the function in order to complete this kind of problem. But it's nice to visualize at the beginning to kind of understand what we're trying to do. All right, so now let's talk about how we estimate this. I'm going to start by looking at the x values here from 0 to 2. And I'm going to break it up into 4 subintervals. So I would do that like so, and we could say that delta x is going to be b minus a over n. B is 2, a is 0, n is 4. That's going to be 1/2. So the width of each interval is going to be 1/2. If we put it all together, we're going to have a 1/2 here, a 1, a 3/2, and a 2. And these are our boundary points that we're going to look at to find function values of. So here we have 4 different subintervals. We have 1, 2, 3, and 4. 4 subintervals, 4 rectangles that we're looking at. And the left Riemann sum says that we're going to use the left endpoints of each of those intervals. So we're going to look at the first 4 points instead of the last 4 points there. And our left Riemann sum, we're going to say that this integral, the actual area, is going to be approximated by this left Riemann sum, where I'm going to take the function value evaluated at 0 times delta x plus the function value at 1/2 times delta x plus the function value at 1 times delta x plus the function value at 3/2 times delta x. And note that we could factor out a delta x out of each of these, and we're left with f of 0 plus f of 1/2 plus f of 1 plus f of 3/2. And the question is, what is f? Well, f is this x squared minus 1. So I'm going to plug those values into that function. We know that delta x is 1/2. Plugging in 0 into that function is going to be 0 squared minus 1. Plugging 1/2 in is going to be 1/2 squared minus 1. Plugging 1 in is going to give us 1 squared minus 1. And 3/2 squared minus 1 at the end. If we have a different function, we're going to have different values there for each problem that we do. So now simplifying, we have 1/2 times, here's a -1, plus 1/2 squared is 1/4. 1/4 minus 1 is -3/4. 1 squared minus 1 is 0. And 3/2 squared is 9/4. 9/4 minus 1 is going to be 5/4. So combining -3/4 and 5/4 is going to give us 2/4 or 1/2. 1/2 minus 1 is going to be -1/2, and we have an answer of -1/4 as an approximation for our integral. And again, note that we did not use the picture to find that value. If we did think about the picture, because sometimes it is nice to think about things graphically, let's draw it carefully here. We have here's 1/2, 1, 3/2, and 2. And let's draw the rectangles that I'm actually finding. The first one is I'm going to look at the function value at 0. I'm going to go down. That's going to be a negative area and go to 1/2. The next one, I'm going to go to 1/2, go over to 1. The next one's going to be a positive area. Or sorry, next one's going to be a 0 rectangle. That's the function value at 1. We saw that before, or saw that. And the last one is going to be a positive area rectangle, 3/2 to 2. And we're adding the areas of all 4 of these, where one of them is just 0. So the area of those 4 rectangles, the height of those 4 rectangles correspond to the 4 values inside the parentheses to the right. And then we have the base is the same for each of those, so times 1/2. This is probably an under approximation. Sorry, it is an under approximation because the function's increasing. But we can see it might be an actually terrible under approximation because we have a lot of area that we're not really considering here. So the actual value is going to be more than that, but this is just an approximation of the area. All right, let's do another problem. Use the graph below to estimate the integral from 0 to 5 of f of x. So I'm going to go from 0 to 5. I'm going to try to find a way to estimate this area. And there's lots of different ways we could do it. We're going to use rectangles to enforce this idea of Riemann sums. But, we could do this as a triangle. We could look at, this area right here and say that's about the same thing as the area under the curve. We could, do rectangles, just do one big rectangle or a couple different rectangles. I think what we're going to do is do maybe 5 different rectangles, one for each integer here. And let's do a right. Let's do a left and a right Riemann sum. So the left Riemann sum with n equal to 5. Delta x here is going to be 1. Draw these rectangles. Each one has a width of 1. I'm using the left endpoint each time, all the way to n equals 4, and then I stop. That's as far as I need to get to. So finding the area of all of those put together would be the function, so it's going to be delta x, 1, that's delta x, times the function values f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4. So since we're multiplying by 1, I'm going to get rid of that 1. I'll just write it right there. F of 0 is 0. F of 1 is about 1/2. F of 2 is 1. F of 3 is 2. And f of 4 is maybe like 3.25 or something. Let's just say 3.5. That's 7/2. We're just going to make a general approximation there. And if we add these all together, we get 7/2 plus 1/2 is 4. 4 plus 3 is 7. We could also do a right Riemann sum. Maybe we'll use n equals 5 again. Let's draw these rectangles. This is going to be an over approximation. But we're going to have, again, delta x is 1 times f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. F of 1 we said was 1/2, f of 2 was 1, f of 3 was 2, f of 4 was 7/2, or about that, f of 5 is 5. So putting that all together, we get a value of 12. The units here are maybe units squared. We're finding area. So maybe our best estimate is to take the average of the left and the right. 7 plus 12 divided by 2 is going to give us 19/2, or 9.5 units squared. Whenever we're estimating, there's not one right answer. We could have used more rectangles and got a better answer. We could have used less. We could have used triangles, as I said. There's lots of different ways you could estimate it. You didn't have to take the average. But there's one way, kind of nice using integers, we could find an estimate for that area. The last problem, we're not going to do an estimate. We're going to find exact values of these integrals. And that's because we're going to be dealing with nice shapes. So we can find exact values because we have nice shapes. So let's do each of these. We're going to first deal with the integral from -3 to 2. So I'm going to go from -3 to 2, and I'm finding the area from the function to the x-axis. So that is going to be this area here. And maybe I can break it up into manageable pieces. We have this one triangle here. Area of this triangle is going to be 1/2 base times height. That's going to be 1/2 2 times 2 is 2. Then let's deal with maybe this rectangle. Its area is just going to be base times height, which is going to be 1 times 2. That has an area of 2. And then finally, this rectangle right here is going to be 1/2 base times height. 1/2 base is 1, height is 2. That's just going to be a 1. So if we're adding all those together, we're always positive. We're above the x-axis. This first is going to be 2 plus 2 plus 1 is 5 units squared, and that is exactly the value. Notice that we had a 0 area for that first chunk because it was just on the x-axis. There's no area there. Now let's go from 0 to 4. So we're going to look at from 0 all the way to 4. We're going to have these two chunks in there, and then also this negative chunk below the x-axis, which is going to be a part of a circle. So we already know that we have these positive chunks, this 2 plus 1, the rectangle plus the triangle. And then this area right here is going to be negative a quarter of the circle. Area of a circle is pi r squared. We're doing a quarter of that. That's going to be negative 1/4 pi, and the radius here is 2 squared. So that's going to be a negative pi that we get there. This is going to be total 3 minus pi units squared. And finally, let's deal with the integral from -2 to 6. That's going to include all of this stuff. It's going to include this half circle, and it's going to include that other part of the half circle, which is also going to give us a negative pi. So total, we're going to have a 2 plus 2 plus 1, and then a minus 2 pi, or a total a 5 minus 2 pi units squared. So we have nice shapes like triangles and rectangles and circles. We can find the exact values of these areas. But of course, we're going to deal with functions that don't have that. And we're going to really explore that more in the next section.